I'll indeed be talking today about one of my lines of research, my line of research on adaptivity, on optimal learning. And it's a line of research that I've been working on for over a couple of years and that I've been doing with a lot of students and a lot of PhD students. And I especially want to mention at the start of my lecture, although my name is here, that for example Florian Sensi has been incredibly important in shaping the ideas that I'm presenting here today. Now, I want to talk about SlimStampen, about rugged learning. And at the end of the presentation, I'll give you an example of how you could use it in your own classes by following this URL and going over a couple of steps. So if you want to do that in the meantime, quickly read slimstampen.nl/app.html and you can install it if you want. Now, what is it that I'm interested in? I'm interested in the optimization of the learning of facts. And that is not because I think that facts are very important in university education, but I do think that if we can optimize the learning of facts, more time remains for the truly interesting things, for the learning of big theories, for the understanding. But for that, you'll probably need to have some facts. Now, if you look into the literature about fact learning, there are two main effects that quickly surface. And one, of course, is the spacing effect. Probably all known by you either from your first or second year psychology classes, but also for me, for example, from my high school teachers, who always said, don't wait with learning until the very last moment, but space it out in time. Information is better retained if the duration between learning events is increased. Now, this is the one main effect. The other main effect is the testing effect, slightly less known, but also sort of like communicated to me by my high school teachers. Be active with the materials. Information is better retained if a learner actively and accurately recalls information instead of merely reading it over. So it's not just about trying to recall it, but the testing effect also states that you need to be able to still recall that information. Now, these two principles are key to optimizing fact learning. And they also have been used quite a lot in literature. And if you look at the literature, this is sort of like the main picture that emerges. People have been trying to optimize recall at a test by looking at what the optimal study gap is. So if I have a test on Friday and I learn on Thursday, should I then also learn on Wednesday, on Tuesday, or on Monday? Now, the big issue with these results is that this component is of utmost importance to determine what this component should be. If the test delay is just 1 hour, you should cram everything in those last couple of hours that you have, because then you'll get the highest grade. If you actually want to learn for something that you still want to recall a year from now, there should be about 3 weeks in between. Now that means that the only way to answer this question is to first ask how long, at what point in time do you actually want to know this information? And that brings a problem to trying to optimize learning. So what we decided to do instead is not so much look at this scheme, but see if we could use these same principles within a single session. So just try to optimize the learning within a single session. So the question then becomes, how can we determine the optimal schedule for within session spacing? Let's say that we have a set of items, a set of French, English word pairs, and we want to order these in such a way that we get the optimal learning. Now, to do that, I'm going to give you a very short introduction into ACT-R, a cognitive theory that you can use to model human cognition. And I'm going to make it very lightweight, because I'm just going to focus on a declarative memory component. And of that, I'm just going to look on one particular formula. And I'm not even going to talk about that formula, because I'm just going to show you a picture. The idea is that when we present a particular item to a learner, that item has a certain level of activation. A level of activation that is very high, but very quickly the activation will drop, of course. If I present you the item again, you get another one of those traces, a very high point of activation, and then a quick decay. You can sum those together based on that summation sign, and that is great because then if we present an item multiple times, the activation will get higher, and you can also see that the slope is shallower. And that is good because, of course, as you all know, there is something like a retrieval threshold, which means that if information drops below that level, you probably can't retrieve it anymore. Now, this figure also indicates that the most simple, straightforward way of learning information is probably not the best way. Because if we would do maximum spacing, so those 5 items, repeat the 5 items, repeat the 5 items, you get exactly this pattern, because there's an equal distance between repetitions. But in this particular case, we would have needed an earlier rehearsal for the very first fact. It's below the retrieval threshold, we fail to retrieve it, and therefore we forego the benefits of the testing effect. But a similar problem we have for those later presentations, because there we present an item although it is not close to the retrieval threshold yet. So we probably should have waited a bit. Now that means that what we want to do is balance the benefits of increased spacing against the disadvantages of too long intervals. In other words, it needs to be just right. And based on these models, that's actually pretty easy to determine what is just right, because we can just follow these curves and decide that we need to have some form of incremental spacing. Just present the item again if it's about to drop below the retrieval threshold. Problem solved, one would say. Well, as you can see over here, this has already been proposed more than a century ago. And it never really took off. And why did it never took off? Well, these are a very nice set of lines. But this assumes that every fact would be equally difficult for any learner. And that's of course not the case. It isn't the case that each fact is equally difficult. It isn't the case that each learner is equally capable of actually learning information. So if this is the prototypical example, then this orange line would either be a better learner or an easier fact. So the question then becomes, how can we determine these individual differences? How can we figure out whether this item for this learner is the black or the orange line? Well, existing methods all use correctness. When an item is responded to incorrectly, repeat it sooner. And this works well, you could say, but at the same time, we already know that this forgoes this testing effect. And the other thing is that you can do the math behind it, and it shows that if you want to purely do optimized learning on correctness, you need to ensure that people make many errors. And that's of course hugely detrimental for any motivational issues. But there is another example, another potential way to actually extract how much people know. Because if I would ask you, and this is my standard example, what is the capital of France? I hope that you would all quickly say Paris. But if I ask you what is the capital of Bulgaria, most people take a bit longer, but then actually know that it is Sofia. Now this difference in time between the one answer and the other answer can be used to figure out when we should repeat items. We can use the latency. When an item is responded to slower, repeat it sooner. Now, and that can of course very nicely be captured by this mathematical model. Because here on the left side we have the activation value, but this activation value can be directly mapped onto response times. And notice here that faster response times are on top. So if we have a particular item and we assume that it decays, we present that item just before we think that it is at the retrieval threshold, based on the default decay value, we have a predicted reaction time. But if we then observe that someone is faster, we know we can sort of like go back and figure out that this item should have had that level of activation, which means that it should have had that decay curve. And that means that instead of repeating that item after about 100 milliseconds, we should repeat that item after about 180 milliseconds. Which, if you think that these learning sessions typically take somewhere between 8 minutes and 20 minutes, is a huge difference. So that means that in principle, we can combine these century-old spacing and testing effects with modern-day mathematical models of human memory to optimize learning. Because we can figure out per learner for each fact how difficult that fact is and thus when to present it. But it's great. Theory always works beautifully. But does it work in real life? What we did is that we went to high schools and we participated in French classes. And we presented students 20 words of a chapter that they were about to learn the next week. So materials that they haven't seen yet, but that were sort of like at the right level of difficulty. We let them learn for 15 minutes on those 20 items, and the next day we came back and we asked them to do a paper and pencil test on how many items they still could recall. And this is the flashcard learning system, so not the optimized system. The flashcard learning system is something that you might all be familiar with. You separate all the items into different stacks. You repeat the items. If it's correct, you immediately go to the next one. If you do an item incorrectly, you put it down on a stack next to it, so that later you can repeat those items that you did incorrectly before you continue to the next stack. This is default flashcard learning. And this actually is already a pretty good method. Because if items are easy, there is longer spacing. If items are more difficult, there is shorter spacing, but it's based on correctness. Now the other method is the optimized learning equation, and what you can see here is that we get an increase of about 15%, or about 1 full grade point difference. And that's huge, because we already started out at about an 8, and these students got about a 9. Now this result is almost too good to be true, so the year later with a new group of students we went to another set of classes with a slightly changed algorithm, but in essence exactly the same, and although that class was not as good as this class was, the results are still very similar in qualitative terms. We get about a 1 grade point difference between the optimized version and the flashcard version. And remember, the only difference here is the order in which the items are presented. Is it based on this flashcard algorithm, or is it based on the latency algorithm that tries to figure out what the state in your mind is of these facts? Now the great thing is that it doesn't just work for vocabulary, it also works for image-based learning. We've done brain regions in SONA experiments. But it also sort of like nicely works for more complex items. For example, what we've done is that we've taken Biopsychology, the first 3 chapters, took out all the definitions of it and had people learn it. And we had them come back on 3 different days, on Monday, Wednesday and Friday. On Monday they could learn chapter 1, on Tuesday they could learn on Wednesday they could learn chapter 1 and 2, and on Friday they could learn chapter 1, 2 and 3. In the flashcard condition, they were allowed to select themselves which chapter to learn. In the SlimStampen condition, SlimStampen determined whether they were ready to continue with the next item, because items are only introduced when the system thinks that you know all items correctly. So in the SlimStampen condition, in the adaptive condition, most students didn't see all items of chapter 3. That's important to keep in mind when I show you the data. And this is the data. So in the flashcard condition, most of them saw all items. In the adaptive condition, most of them didn't see all items. But still what you can see is that the whole distribution is shifted upwards. It isn't just that the better students get a lot better or the worse students get a lot better, but there's really sort of like this shift. At the same time, you can also see if you're a good learner, you're a good learner and it doesn't matter that much. And also here we have learners that just completely fail in a way at this task. But the nice thing here is that even though most of these didn't see all items, they clearly outperform the other condition. So it works. It really sort of like worked to take these century-old ideas, implement them in a computational model and test them in real-life settings. Whether it's high school vocabulary learning or it's sort of like our 1st or 2nd year courses where students still need to learn many definitions. And it's actually very nice because this is sort of like the pragmatic approach. But we can also do a lot of research with this because, for example, we can very nicely look inside the model. This is the rate of forgetting expressed as the internal parameter that captures the rate of forgetting. And this is a very first item that is done a couple of times, and then here at this point in time, the system thinks that the learner knows the item well enough and it doesn't need to be repeated. And we can look at that for all different items. So this is, for example, an item that the learner found more difficult. So it's repeated more often. But then at some point you see that the rate of forgetting goes down, so the learner becomes better, and apparently it sort of like figured out what that item was. And then at this point in time it again says, well, you've now seen it enough. And you can do that for all these different items. And for example, in principle we could start to look at sort of like motivational issues, because this apparently is a very difficult item. But we could also, for example, say, well, maybe it's better for this learner to just forget about learning this item. This learner might never be able to score a 10. Let's then focus on those items that it can learn. And so you can look at all these different items and come up with a list of the items that on average for students are difficult or easy. Now, the other thing is that this rate of forgetting that is assessed during learning also has a very high correlation with test performance. So I'm willing to argue that we probably could get rid of tests and just measure the learning, and that the learning gives maybe even a better estimate of what people know than the actual test. So I would say, if fact learning is required, it's truly a shame not to use these types of personalized adaptive learning systems. Now, I'm not alone in thinking that this is just a great thing, because, for example, Nordhoff Publishers also has implemented this idea, and it's now being used by about 500,000 high school students to improve their fact learning, something that I'm incredibly proud of, because these children will now learn their facts better due to the work that we've been doing in our labs. But the great thing is, and this is where the PR part starts, it's also available as an app by now. Based on an e-learning grant of the university, we've been able to develop this app, a web, iOS and Android app that can be downloaded, and it is integrated with Nestor. So we've been using it, Ritske de Jong and I, in our courses, and students really like it. And it's available for any course that has a Nestor component. And if you want to use it, there are just 3 very simple steps. The first one is to create an Excel sheet with a list of definitions and the answers associated to this. What you can see here are famous RUG professors or alumni. Then you go to Nestor, you select Assessments and Rugged Learning chapter. It's a very simple form with a title and an upload button, and where you need to indicate whether this is free-form typing or multiple choice. And that's it. You log in to the app. You select the chapter that you want to use, you select the time that you want to learn, and then you get definitions like this, and you're being asked to give an answer. Professor of Chemistry, initiated chemistry is an independent science in the Netherlands. Is that Anda Kerkhoven, Johan Bernoulli, Pedros Listen, or Bernard Reuling? Now, for anyone who doesn't know, you can download this app and start practicing today. It is Pedros Listen. Now, the nice thing, of course, is also that this is linked to Nestor. So what we could do is, for example, assess how long do our students actually learn? What is the length of their learning sessions? Which, very much like high school students, seems to be about 8-9 minutes. We can assess when they were actually learning. And as all would expect, there aren't that many students starting before 9 a.m. And actually, at 11, you get to the point in time where most are active, but then it's really time for a coffee break. And if you look at those here, which is learning in the middle of the night, yes, that is indeed the night before the exam. Now, of course, this is hugely skewed by motivational issues, but students that did use our system scored much higher on the exam. And I'm not going to say that this is due to the system, because of course the better students are going to explore any option that is available to them. But still, it's nice to see that it's in that way. But even if you look at the amount of time that they spend in a system, there's a very direct link between the time spent in the system and the actual grade that they got on the test. So summarizing, I think that we can make a difference. We can make learning stupid things. And trust me, I hated learning facts at high school and at university. But we can make that easier and better. And that due to implementing psychological theories into something that can be used in the real world. Thank you for your attention.